There we go.
Just let me know. Good afternoon. Okay, so the week of October 12th, that's where we're headed for now. We're going to be doing the standardization of a solution via titration. Okay, so first of all, what is standardization? Standardization is determining the concentration of a solution to a high degree of certainty. In other words, we really know the accuracy and we really know the precision very well. So you're going to have to be on your best behavior, come in ready, and be very, very careful, or you're going to be here forever. So we're going to be determining the concentration. Now you should be 3 lectures into chapter 4, so you should know what concentration is by now. But the concentration we use most frequently in general chemistry lab is molarity. And we represent the molarity of sodium hydroxide, which is actually what we're going to be standardizing this week. Sodium hydroxide we represent in brackets, not parentheses, in brackets. So this represents the concentration of sodium hydroxide, which is molarity. Molarity is simply moles of a solute per liter of a solution. Now, I'm not going to write it on the board because you should know this from high school if you haven't listened to the lectures this far yet. A solution is always made of 2 parts. One is a solute, and that's the substance that's in the smaller amount that is dissolved. The second part is the solution. That's the substance that is in greater amount that does the dissolving. Now, when you make a certain concentration of a substance, it's the moles of the solute, stuff that you're dissolving, in the volume of the whole solution. Why not just use the volume of the solvent? Well, because when you add solute to the solvent, the volume increases. Okay? So we're going to be looking for the molarity, the moles of a solute in a liter or per liter of solution. So what's the point of standardizing anyway? I mean, if I'm going to sit down and make sodium hydroxide solution, why can't I just find some grams of it, convert it to moles, and then put it in a certain amount of water to make 1 liter? Why wouldn't that work? Well, we need to standardize many, many substances for 3 reasons. One of those reasons is that the substance can be very, what we call, hygroscopic. Hygroscopic, which means it absorbs water super, super fast. Okay? So sodium hydroxide is actually a solid. You've all seen Drano. Well, Drano's got other stuff in it, but it is effectively sodium hydroxide. It's a solid, but it's also really, really, really hygroscopic. It absorbs water super, super fast. So literally, by the time I got some sodium hydroxide pellets onto my analytical balance, I'm going to be really good and make this mass as accurate as I can, as precise as I can. Put it on the analytical balance. By the time I write down the mass, that sodium hydroxide has already absorbed water. So I have no idea how much that mass is of sodium hydroxide and how much is water. A second problem can be that a substance can decompose. Substances can decompose when they're just sitting around as solids or liquids or even gases. They can decompose very quickly. So what we need to do is get it into solution as fast as possible. But again, that mass that you've got to find the moles of your solute can be, by the time you actually get it into solution, partly your substance, your solute that you want, and partly those decomposition products. So again, I'm not going to know accurately the moles of my solute. Third is an awful lot of solutes that's impure. An awful lot of solvents, an awful lot of solutes are impure. We can't get them so that they're 100% of whatever substance we want. So again, the mass of that substance that I weigh out is maybe 90% of the solute I want, and maybe 10% of impurities. We don't know. So generally, what we do is a substance that we use to make a solution. If we know it's hygroscopic, or that it is unstable, or that it's impure, then we need to standardize it. Okay, so now we know why. Let's figure out how. There we go. So NaOH, as you know, is a strong base. We're going to be standardizing it by using a neutralization reaction. And the neutralization reaction is going to be using, obviously, an acid, since we're standardizing a base. Now, in order to have a good neutralization reaction, we have to have an accurate number of moles, in this case of acid. How do we do that? Well, we choose a primary acid that, 1, is not hygroscopic, 2, does not decompose, 3, is not impure, and there's another one in your Prelab book that you can see. But anyway, the one we choose is potassium hydrogen phthalate, that we abbreviate KHP. This is a weak acid. Here it is. We have 6 carbons that are alternatingly double and single bonded, and on the sides of each of these we have a carboxylic acid group, or a carboxyl group. In this case we have the hydrogen, and that's our acidic proton. This is the one that's going to come off during the chemical reaction, during the neutralization. This one's already off, already in a salt form. So we have 1 hydrogen. This is a monoprotic acid. 1 hydrogen. Okay, so we're going to be using this. High degree of purity, high molecular weight, very stable, and not hygroscopic. So let's see what we're going to do with it. I need to go this way. All right. What we're going to be doing, I'm abbreviating KHB as HA, just means that's a weak acid. Okay, it shows the hydrogen, and A stands for that whole mess. So HA plus NaOH. You can see we have a 1-to-1 molar ratio. And at the equivalence point, it means I have an equal number of moles of weak acid as I have of base. We're going to figure out how we know that in just a minute. Well, we have to use stoichiometry to do this, and this is why you need to have read Chapter 4 or watched the Chapter 4 videos. In order to figure out what the concentration is of NaOH, we're starting with a mass of the solid KHP. Using the molar mass of KHP, which we've done for you, you can figure out how many moles of KHP you have. Now we are going to convert from moles of KHP to moles of NaOH. We're going to look at these calculations in a second. And we're going to get our moles of NaOH. Now we can use the volume that we're going to get to find the concentration. Okay, moles per liter. All right, as an example here, I'm going to take 1 gram of KHP, and I'm just going to say that's what I actually have, and I'm missing a 0. You can have your 4 decimal places. And here is my molar mass of KHP, 204.2 grams per mole. So my grams of KHP cancel, and now I have my moles of KHP. I don't want to know moles of KHP, I want to know moles of NaOH, because that's the concentration I have to figure out. So I take my moles of KHP that I just found out, and I have 1:1 molar ratio. 1 mole of NaOH to 1 mole of KHP. My moles of KHP cancel, and I'll now be in moles of NaOH, right here. Now, all I need is this volume of NaOH to find its molarity. Super! Where do I get the volume from? Do I get the volume from, oh, I don't know, the solution bottle? No. I get the volume from the titration. What? You're going to be titrating this acid with this approximate base. You're going to be titrating it. And at the end point, when you've got, at the equivalence point, when you've got the exact same number of moles of acid and moles of base, you will know the moles of base that you have used. The base is going to be in the burette. Base burette, okay? The base is going to be in the burette. You're going to be titrating your acid in the flask below it. When we reach the equivalence point, you're going to read the amount of base that you have added. It's going to, remember, be in 4 sig figs, 2 numbers and 2 decimal places, right? And you're going to convert this to liters. It's in milliliters when it's in the burette. You're going to convert it to liters, and that's the volume you'll be using. Don't worry, we're going to go back over the calculations before you actually pass this in. But you're going to have to be able to do these calculations in lab, because you're going to have to keep doing these titrations until you get 3 that are really close in the molarity. Okay? So finally, how do we know when we've got this equivalence point? Well, we have something called an indicator, and an indicator changes color at a certain pH. Okay? So the indicator that we're going to use, and I'm not going to try to write it out because it's tough, is phenolphthalein. And phenolphthalein, I always miss 1 or more H's in that word. Phenolphthalein is colorless when it's in acid. Okay, so you're going to put it in here at the beginning. It's going to be colorless. And you're going to add this colorless base, more and more and more, and boom, you've hit the equivalence point, and all of a sudden, it's pale pink. It better not be fuchsia. If it's fuchsia, you're starting over. Pale, pale, pale pink. Okay, if it's fuchsia, you've added too much base. You have no idea how many moles of base you've added. Pale, pale pink. Colorless and acid, pale pink at the equivalence point. When you know this is 1:1. When you know your number of moles of acid is equal to your number of moles of base. Okay, so this is going to be fun. Calculations are easy once you get used to it. Be careful, and we'll see you in lab.